Hey guys, this is Venci, and today we'll be covering proof by induction. Uh, so this is something I covered about a year and a half before I went into university. It was at A level, or high school in America, I guess. Um, but the point is, it was a proof technique where I didn't really understand why we're proving the statement for n equals 1. Why are we just allowed to assume whatever we assume? And how does the proof actually work? Like, I didn't get the logic. And then I went to university and I covered some basic university math. So this is about logical statements, about, implications, as you'll see in just a second. And those are ideas which every mathematician at university covers. And they're very useful. And I believe they extend to outside of math. They extend to just logic. And that's, something that occurs every day. Anyways, so let's get into it. Let's say we have this simple statement here. If x is a cat, then x has 4 legs. Now, of course, a cat could have lost a limb and it would have 3 legs. Maybe the cat had a birth defect, but we're not going to look too deeply into, cats and like how many legs they have. The point is that the species of cat have 4 legs, right? Um, the way we would express this sentence, this logical relation in mathematical notation is like this. X is a cat implies that's what we call this arrow implies X has 4 legs. Now this arrow, the standard way to write this arrow is very important that you write it as a with 2 barrels, so it's almost like an equal sign and then a greater sign tacked on at the end. And this is standard mathematical notation. Anybody who went to university to study math, when they see this, they'll recognize what this arrow means. It's standard notation. However, let's now assume the contrary. X has 4 legs implies X is a cat. Well, this is just not true. If X has 4 legs, X could be a dog. X could be any animal which has 4 legs. So the way we would write this is that X has 4 legs does not necessarily imply X is a cat. Of course, it could. We're just saying that this doesn't necessarily imply X is a cat. There are more things which have 4 legs. So just because one thing implies the other does not mean that the other implies the first. Now let's look at another case. So if X is a cat, then X is a small domesticated carnivore bred in a number of varieties called Felis domestica or whatever. Now this is just a standard dictionary definition for a cat. It's just one of the definitions, I just didn't want to write out a whole page of dictionary definitions for a cat. So I just summed it up to this one sentence. So this is essentially the definition of what a cat is. So obviously, if X is a cat, it must fit this definition because this is the definition. Um, so that's fairly obvious. But also, we can say that if X is a small domesticated carnivore, bred in a number of varieties, then X is a cat, right? So not only does X is a cat imply the definition implies that X is a cat. Now, in the previous case, we saw that when we switched the two statements over, this implication didn't hold, but now it does. And that's something very special. We say when this occurs that these two statements are equivalent. X being a cat is equivalent to X fitting this definition of a cat. And when you think about it this way, it's fairly obvious. And this is the definition of a definition. This is what it means for something to be a definition. It means that the definition implies the word, and the word implies the definition. And the way we write this creatively is just as an arrow with like a less than sign on one end and greater than sign on the other end. It's just an arrow pointing both ways. And again, this being a double barreled like arrow with like, the equal sign, that's important. That's the standard notation for this. But we're not going to be focusing too much on the double arrows. We're mostly going to be focusing on implications. That's all we need for to understand the logic for the proof by induction. So let's get into it. So the proof by induction procedures are as follows. The first thing that we need to do is the base case, is to show that the statement holds for n equals 1. Now, sometimes this will be n equals 1. In most cases, it will be n equals 1. However, sometimes you could have it n equals 0. It depends on which numbers we're showing the statement for. Sometimes we might want to show that the statement holds for 0, 1, 2, 3, 4, 5, 6, 7, 8. In that case, n would be 0. We might want to show it for n equals -2, -1, 0, 1, 2, 3, 4, up to infinity. In that case, it would be n equals -2. It's just the first number, the number from where everything starts. But you don't need to worry about that because in most cases you're just dealing with n equals 1. The next step after we've shown this, and that's literally just plugging the number 1 into the equation and showing that it holds, the next step is the induction assumption. So you might have seen this worded a bit differently, and perhaps that's what confused me, but this wording to me is the most clear. So I'm just going to say it as it's written here. Assume that we're given an integer k for which the statement holds, right? So this integer here, we don't focus on what it actually is. We don't think about what the actual number k is equal to. We just treat it as a generic number, any number k for which the statement holds. Now, we know that the statement holds for n equals 1, so k could be 1, right? It's any number, this can be any number for which the statement holds, and that's all we know about k. And our job is in the inductive step to show that the statement holds for the next number, k plus 1. And finally, we just write out a conclusion, and this concludes the proof. So why does this proof work? Well, let's think about it. Let's go back to our logical notation. Statement holds for k, right? That's what we assume, that's what we have here. This is a reasonable assumption because we already have some number for which this statement holds, n equals 1. And we're assuming that we're given some integer k for which the statement holds. So there is at least one number which this k could be. It could be 1. It could be other numbers as well. But for now, we're only sure about 1, right? So let's see what happens. And assuming that we're able to show this inductive step after we do the algebra, which we'll show in the example video for proof by induction, after we've shown the algebra, we know that the statement also holds for k plus 1. This is our job, to prove that this implies this. So when we plug in 1, because we've already shown that when we plug in 1, the statement holds for 1, then we also get that the statement holds for 2. But also, now that we have that the statement holds for 2, we can plug it in because k can be anything. We've just shown that given any k for which the statement holds, it also holds for k plus 1. We also have that the statement holds for 3. And then we can plug in 3, and I think you see where this is going. The statement holds for 4, and so on and so on and so on. And we show that the statement holds for all integers. So this is the logic of the proof. And if you understand this, if you understand how the proof works, then you can explain the conclusion in your own words. Try and construct like a few sentences explaining how the proof works, as an exercise to sort of to test whether you actually understand the logic and whether you can write it down. So I hope you found this video useful, and I'll see you guys in the next one. Take care.